Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Tom Wagg and Katelyn Breivik with us today. Hello, Tom. Hello, Katie.
Hello.
Katie, let's start with you. What's your geolocation?
I right now I'm in Pittsburgh, Pennsylvania. I'm at
Very,
Carnegie Mellon
very
University and
cool.
I'm an assistant professor.
Very cool. Congratulations on that.
Thanks.
And is spring in the air in Pittsburgh? Or are we still in our winter mode, kind of?
No, we're in very sad winter mode
Very
right now.
sad
Everybody's
winter mode.
ready to be done.
Okay, well, at least the plants behind you are doing okay. So,
That's right.
they're hanging in. And Tom, how about you? What's your current geolocation?
I'm in Seattle, University of Washington, and
Uh-huh.
yeah, I don't know how spring's doing it for us, but it's cold, but it's not raining, so we'll take that.
Seattle. I'm actually going to be in Seattle in about 1 month. I'm going to the INT. So,
Oh, nice. You're just one floor away from us then.
oh, yeah, 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 exactly. So I'll swing by and introduce myself in person and all that stuff.
Perfect.
Very
Yeah, I
cool.
look forward to
Very
that.
nice. Oh, and Tom, what do you like to do for research?
I like to do binary stars, anything kind of related to binary stars. I've kind of like hopped over all sorts of different things while I've been in grad school. But it's whether it's relating to like gravitational wave sources or thinking about like astroseismology as well. But yeah, any way that I can try and understand how binary interactions work, that's something I'm excited about. Which is
Very cool.
yeah, this more recently it's been kind of connecting it with dynamics as well. So that's
Yeah. Well,
that's kind of where I'm
we'll get to that. Actually. Cool. And Katie, how about you? What do you like to do for research?
Uh, Same general vibes, I would say. Binary stars, binary star interactions. I like to spend a lot of time writing code that other people like to use. I love to see what other people do with the code, cosmic.
Mhm.
And yeah, my focus is often on gravitational waves, specifically a lot of LISA stuff. I'm really excited about LISA.
Very cool. Very
Yeah.
cool. And that is going to bring us to this very awesome APJ supplement article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one.
at.
Cogsworth, a gala of cosmic proportions, combining binary stellar evolution and galactic dynamics. And Tom and Katie, take us away.
Yeah, so we had a lot of fun with this. You can see we have from the people on the author list we have a nice array of expertise here, where we've got Katie is coming in with cosmic and the pop synth side. Matthew's there, University of Arizona as professor doing all sorts of binary evolution stuff and also more detailed evolution. So it's great to have that. Of
Mhm.
course, Adrian's coming in with all of the galactic dynamics expertise. He's
Yep.
the author of the Gala open source code, which I'm sure we'll get to. You can see it in the title. And so kind of like by their powers combined, I have all of the wonderful co-authors to kind of come up with something like Cogsworth.
Very cool.
Yeah, so it's been good fun. I feel like before I say anything else, I should point out it's not an acronym. It's just a thing that I think is fun to say.
Sure, absolutely. Very cool. If
It's just it's supposed
it
to
had
sound
some literary
approximately.
background, right? Some 1850s literature or something.
Yeah, no, it's just like it's supposed to evoke Butler English
Yeah,
vibes.
yeah, exactly, right?
Yeah. But yeah, it's
Very
it's
cool.
it's this yeah, so it's basically this new open source Python tool that will do self-consistent pop synth with galactic dynamics at the same time. So what that means is you can do all of your usual binary population synthesis of, you take two stars at some initial time, evolve them forward, see how they interact, but then at the same time, you put them within a galactic context.
Yeah.
And so then you can move them through a potential, see whether they disrupt, see where either star ends up. And at any point in its history, you can say, where is it in the galaxy? What is its orbital period at that point? And what is its mass?
Does
And
it still exist?
does it still exist? Is it still a star? Is it just a
Right.
black
It
hole
may
now?
be gone. At
Um,
least one of them might be gone. I don't know.
right. So yeah, has it merged? All of those
Ah, there we
things
go.
kind of
Yes.
go into it.
Uh-huh.
And
Cool.
yeah, so there's a couple of different parts to it here. One of the thing that it does is kind of combining hydrodynamical sims as like a post processing thing. So you can
Right.
take their simulation, and maybe I'll talk a bit more about that in a moment. But yeah, this is basically just going to go through and show you a bit about how the code works, why the code is around, and some examples of how you can use it.
I want to point something out here about this abstract. And you'll see it several times as we go through the article, people. You'll see these little pencils down here. Tom, what do those mean?
Yeah, so basically throughout this, there's going to be connections to the documentation of Cogsworth and also just the GitHub. So anytime you see a pencil in a plot, it will basically, in this case, it just links to the GitHub and the documentation. But for each of the plots, there's a little pencil, and then you click on that, it'll go to a page in the documentation, which is the same sort of plot. There's maybe a different initial random seed, but the same vibe, and then the code to reproduce it as well.
Very cool. Very cool.
Yeah.
The other thing I'll very quickly point out is that this is a flagship example of a collaboration between AppJ Supplements and the Journal of Open Source Software, JOSS, which has become, I would say, very characteristic of Tom's work, where all the code that Tom writes also gets reviewed. All of the software Tom writes gets reviewed as well through peer review, which I think is a really excellent tribute to his dedication to the open source community.
Well, you won't get any argument from me out of that.
I mean, it's something that I appreciate as well. It's like I every time I've gone through one of these reviews, I think the code has got a lot better. Like having those extra eyes on it is so useful.
Absolutely. Absolutely. Very cool. Okay, let's go ahead and go into it here.
So yeah, it starts in the way I like to start pretty much every paper, which is pointing out binaries are everywhere. The majority of these massive stars are going to be in binaries. They're going to be interacting at some point, and that's going to change their binary evolution. And an important part of that is it's not just changing, how the intrinsic properties of the binary are changing, how the stars' masses and orbital periods are changing. It's also changing where they're going to end up in the galaxy. Because, your single massive stars, they're not going to migrate very far from their birth locations. They're going to live fast, they'll die young, and they'll die close to where they're born. But, if you're in a binary star, then if your primary star explodes and then the secondary star the orbit is disrupted, the secondary star is ejected, it can end up, very far away. You can get runaway stars. And so what you see are these, like, many massive stars and compact objects in weird places or with reduced spatial correlations to star forming regions. So what it would be nice is if you had a pop synth code that connects with a dynamics code so that you can actually make predictions for this and compare to all of the observations. And actually start to maybe put some constraints on parts of your binary evolution based on the positions in kinematics. That's kind of the motivation of why you'd like to have a code sort of like this.
Cool.
And I mean, the idea itself is not, not brand new. It's you can see kind of in that the final paragraph on the right hand side. There's a lot of other people who have done similar sorts of ideas of including a potential and accounting for the kinematics. It's been done in different ways. Like lower down, the series of Repetto papers there are kind of retracing the orbit and finding the first time it crosses the disk of the galaxy to try and say, okay, maybe it probably formed there. But maybe not accounting for the fact that
the hypervelocities. Yeah.
Oh yeah. And these are all generally like excellent but bespoke kind of ways of modeling this, which are great for those particular cases, but maybe not for a general use case. I should actually highlight as well the Jeff Andrews and Vicky Calagera paper there, 2022.
Yes.
That was kind of so that was basically trying to constrain natal kicks based on the microlensed black hole that was detected.
Right.
And that microlens detection is actually kind of what motivated us to make Cogsworth in the first place. We were basically trying to do the same thing, and they did it first and excellently. And then we were like, okay, we can't necessarily do this modeling just for a microlens source. What if we made it a bit more general? What if we made a code that works for more than just this one thing?
Right.
I think it was Mathieu that first said, what if we did a galaxy of binaries? It felt very dramatic to me at the time. We're
less so now.
Less so now. It seems less impossible. But yeah, you can see lots of people have done very interesting things in related ways. And we've tried to make a kind of general flexible tool that can handle all of those sorts of possibilities so that you can do all of the self-consistent population synthesis and galactic dynamics and apply it to all sorts of different sources, whether they're runaway stars or X-ray binaries, gravitational waves, gamma ray burst progenesis, all sorts of different things you could do in the same simulation. And that's a useful thing because you can imagine if you want to constrain supernova natal kicks, and
Mhm.
in order to produce the amount of runaways that you see, you could really crank up the kicks, and that'll disrupt all of your binaries, and it'll give you more situations where you've got ejected stars.
Yes.
But if in the same simulation you're also trying to fit the X-ray binaries, you'll suddenly find you have no X-ray binaries left because you've disrupted them
They're
all.
on. Right.
So by modeling different populations at the same time, you can place better kind of joint constraints on
Yes.
some of the very degenerate parameters in population synthesis. So
Cool. I'm with you.
yeah. But yeah, that's kind of the overview of the introduction. And then, there's just a paragraph there on the structure, but we can kind of get into the code, as it were. And I think this is maybe most easily done if you just go straight to figure 1.
Let's go to figure 1. Let's blow this up.
Because that kind of gives you a bit of an overview of the structure.
Cool. Okay.
And so I'm going to kind of go from the middle up and then down. So
Okay.
Cogsworth itself is basically formed out of 2 main parts, which are exactly those 2. The population synthesis, which is coming from Cosmic as the backend for that, which is Katie's code for doing rapid binary population synthesis. It's kind of an improved version of BSE, fit to single like models from Onopol's.
Yes.
And what it's connected to is Adrian's Gala code, which does the galaxy dynamics. So by those 2 things together, you can start moving your stars around the galaxy. But an important thing with PopSynth is not to just you don't want to do just one model. The advantage of population synthesis is you can run a series of many different variations. That kind of flexibility allows you to see how sensitive your results are to different assumptions that you've made.
Yes.
Because these are, of course, approximations to stellar evolution. We should be very careful and see, don't just use one model. But
right.
Cogsworth allows you to do that. So you can change your initial binary population. So you can change, how do you want to sample that population in terms of your initial mass function or your, mass ratio distribution, eccentricity distribution. And similarly with the binary physics assumptions, what do you want to set for your efficiency of common envelope phases, or how do you decide the stability of mass transfer? Those sorts of settings are all very flexible in here. And I should say this is all coming from Cosmic. It's just that this is kind of a wrapper around that. So anything that you can do in Cosmic in this way, you can do in Cogsworth.
Okay. So is the whole thing, since you brought it up, is the whole thing fast enough so that you could pop it into some Monte Carlo or Bayesian framework?
Yeah, ideally.
So we're talking about
Cosmic in particular is really fast.
Yeah.
The addition of Gala, it depends how long you want to integrate the orbits for. So if it's like, very massive stars that don't live for very long, it's still very, very fast.
Yeah.
It's slightly slower if you're integrating, some low mass X-ray binary that's hanging around for billions of years.
Okay.
But it's still such that you should be able to do those sorts of things. Yeah.
Okay, cool. Okay. Thank you.
Yeah, of course. And yeah, so on the galaxy side, just on the right, what you can do then is change the potential and the star formation history as well. So do you want a Milky Way potential? Do you want a small dwarf potential? You can change the star formation history between, is it going to be where are your stars formed? When are they formed? With what metallicity? And if those 2 things are things that maybe people don't care about or don't feel like they have the expertise to do, what you can do is take any fire or Changa hydrosim and use that as input for these. So Cogsworth is capable of fitting a galactic potential to one of these simulations and also taking the star particles to the recent star formation, use that as input to the simulation.
Cool.
Yeah. Right. And then what you get out is the stuff at the bottom. You get, rates and distributions of your intrinsic population, the kinematics, which is obviously the important part here that we're adding. And we also have, conversions between the intrinsic population and the observable population. So you can directly compare it to what you've observed.
Yes. Very nice. All right.
So yeah, all of these next sections kind of go into these things in a bit more detail. So let's maybe scroll and skip around for some of the bits that maybe deserve a little bit more attention.
Okay. Star formation histories.
Yeah. So the basic star formation history that we've got in there as the default is one from a paper I did in a couple of years ago, which is really mostly based on work of Nesh Frankel. Yeah, that Nesh Frankel 2018, 2019 there.
Yeah, there we go.
So that is accounting, as it says, for inside-out growth, growth. Oops, that was a typo in the galaxy, and radial migration. And
Growth.
Just noticed that. Okay.
well, oh well, it's too late now.
Coming by the copy editors too. Wow. Okay.
There it goes. And that has more detail just for the Milky Way in particular, but there are simpler ones that have, just like bursts and uniform disks.
Yeah.
So you can kind of play around with it, and it's very flexible and modular. So you can combine different star formation histories, or you can like define your own if you really want to.
Oh, nice.
There are tutorials about, I even say explain how to accomplish this in a tutorial. I think I do a completely ridiculous one where I make a galaxy that's a cube.
Very cool.
You can play around with that if you want. But
I'll advertise here that this is a huge development for me, because I get lots of questions over email about how to make Milky Way galaxies with Cosmic. And now I can just shunt them to that link, that tutorial, which is really nice.
Free up all kinds of time, Katie.
That's right.
So we can go on with the future stuff, which we'll get to, but here we go. Okay.
Yeah. No, I feel like that's how I like to respond to every question, is just make a new docs page so that I don't have to answer the question again. Yes. And then maybe just the one important thing there is the second equation is just, so defining the initial position is based, just on those models, but then the velocity, you of course need an initial velocity if you're going to integrate the thing through a potential.
Okay.
And so what we do is basically just take the potential, find the circular velocity at the location that the star is formed, and then add some velocity dispersion, which you can change to whatever you like, but by default, it's just 5 kilometers per second.
Yes. Okay.
Which is approximately what you'd expect for the solar neighborhood-ish.
Okay. Nice.
Yes. Great. And then, sampling and evolution, this is basically going in, I don't know, maybe this will be a thing that Katie maybe wants to talk about, because it's the beauty of Cosmic.
Yeah. So Cosmic handles all of the binary populations in an intrinsic sense. So Cosmic has all of the tools to initialize binaries based on empirically motivated distributions for things like initial masses that are drawn from different initial mass functions. We can assign orbital periods for you, eccentricities, all of that stuff. And we track the evolution through basically every phase from zero-age main sequence to compact object formation and merger. So all of that's handled exactly like you might explain or expect in Cosmic if you've used the tool before. And if you haven't used the tool before,
there's a tutorial.
We worked really hard to make it easy to use. So I would love if you tried it.
2 tutorials inside of a few pairs.
That's right.
We're doing good. Okay.
And as someone who's used multiple different pop synth codes, I will say Cosmic is very good for getting into very quickly.
Nice.
It has a very nice
ease of or low barrier to entry. Let's put that.
Yeah. And also, Kitty, you should talk about the cool thing you have with the dynamic time resolution.
So we have Cogsworth, I think, is a really excellent example of some of the features that we've put in that people don't often know about Cosmic. So in particular with Cosmic, we wanted to make sure that everything was as easy to reproduce as possible. And specifically, if you're interested in one specific binary that has a particularly interesting formation path, and you want to see how that binary changes under different assumptions.
Okay.
We have some pretty slick features where you can go in, select a stage, restart that binary, and run it with a bunch of different parameters.
Okay.
Or if you don't have enough time resolution, you can decide, I really only care about this phase, the AGB phase, for example, and you can get as tight of time resolution as you'd like on there. And that can be especially helpful for resolving things like pre and post supernova evolution. And that kind of thing.
Very cool. Nice capability.
Yeah, no, it's very fun to use. And all of those features are directly available through cogsworth populations as well, which is very fun. Then for the galactic orb integration, this is all using Gala, which is, it's really just wrappers to lots of C functions, so it's nice and fast. Lots of very different flexible potentials that are in there. Everything from, as it says there, the Milky Way, the most recent Milky Way potential they have fit to nice mass measurements in the Milky Way. But but also the usual things you'd expect to see, the NFW profiles, the Plummer potentials.
Yeah, okay.
And you can mix and match as you like. You can it's very nicely written where you can literally do like potential plus potential, and it's then a new potential that combines the two of them. Adrian has a very nice interface for that.
Okay, good.
And then the bit that we're sort of adding to this is accounting for the fact that Cosmic is going to go through and log, there was a supernova at this time, and the change in velocity to the two different components was this, whether it's stayed bound or not.
Yes.
And so what cogsworth will do is integrate the orbit up to that point, and then pause, adjust the velocities based on the supernova, and then continue.
Restart.
In some cases, then produce two different tracks.
The
binary may disrupt into two different stars.
Two parts. Yeah.
Yeah.
Cool.
Yeah. So then you can track the location of your stars at any point in its evolutionary history, and it's all available there, which is fun.
Very nice. Okay. And then we got observables, because we do like those.
Right. We don't just want to live in a make-believe theory world as much as I'm tempted to sometimes. We do want to actually compare to
challenge.
Right? So kind of the main ones that are in there right now, well, mainly it's focused on Gaia observations. So what it will do is take the bolometric luminosity that is reported by Cosmic, and then use the isochrones package, and use that to kind of adjust it into whatever filter that you choose. Okay. And then you can apply dust extinction based on the dust maps package, using whichever dust you like from there. By default, it's just going to use the most recent Baystar one. And then, exactly. And then you can use the Gaia empirical selection function from the Gaia unlimited package. And that will then say, based on the magnitude in the G band and that it's in this location with this extinction, this is whether it's going to be detected by Gaia or not. And so you can see a lot of this is relying on wonderful work by other people. There's a nice, it's really kind of like a nice conglomerate of packages together, hopefully with a regional interface.
Shoulders of giants and all.
Yeah, exactly. I would not have been able to reproduce all this, so it's good that it's all out there. The beauty of open source software.
Exactly.
Yeah. And
so we got electromagnetic.
Right. And then gravitational waves. So Katie and I both, of course, have a love for LISA. And back in the day, when we first started working together, what we made was a Python package called Legwork. That one was an acronym. And that basically allows you to check the gravitational wave strain and signal to noise ratio of any binary that you've got, as well as do the orbital evolution because of gravitational wave emission. But I have now a pretty, I would argue, well, it's one line, a very simple connection between Cogsworth and Legwork to basically say, given my population, which ones have an SNR greater than who knows, 7,
whatever the value is, whatever you said.
Fourier Lie submission. So you can immediately take your simulated population and say, which of these ones am I going to see in LISA? Which, yes, it's fun. Yeah. And then this next part is talking more about building off hydrosims, and first of all, just saying a bit about why it's useful, because it has, built into these, of course, naturally, lovely initial spatial correlations. So, our stars are not forming, alone in the field. They are generally randomly clusters, which, may well dissolve very quickly, but you do have some initial spatial correlations. Yes. And so if, as a tool, we are aiming to, measure the final spatial correlations of our stars, it would be maybe a nice idea if we can get some of the initial things a bit better as well. Exactly. And so this next section is just talking a bit more in detail about kind of the implementation of this. So, the things that it's currently set up with to work with now is just the Fire and the Changa simulations, because those are the people that I know, but I'm very open to doing other ones as well. It's really all kind of working well with the pin body code, which is like a beautiful interface for all these things. Made this a lot easier. That allows us to just kind of prepare the snapshots. So you basically just take the present day snapshot from, or I guess whatever snapshot that you want, from one of these simulations, and then work out where the center is, rotate it so that it's looking the right sort of way, and then we can fit a potential to it using this kind of self-consistent field method, which is basically using a series of basis functions in spherical harmonics to get you that potential.
Yes.
And you can make that as detailed as you like. You can use as many of those spherical harmonics that you like.
You like.
And it will just take longer.
You will.
But yeah, and from that you can then get the initial stellar positions just from the star particles. And so what we do, maybe in this next, I think it's in this next section where we talk about how yeah, exactly. So we take each star particle, in these simulations, it's order of thousands to 10,000s of solar masses.
Okay.
So we need to convert that into a series of binaries. So we do the usual sampling thing that Cosmic does, but in addition, sampling exactly where they are based on some Gaussian centered on the parent star particle, with your choice of radius of how large you would like to make that cluster.
Yeah.
You can then set the virial parameter of the cluster, which is basically telling you how bound is this, and what that's essentially going to do is change the velocity dispersion of the star particle. And so then each star that comes out of the star particle this is equation 4 here, is going to have an initial velocity that is just the initial velocity of the star particle plus the dispersion velocity of the cluster, which is determined from that next equation, which is just basically combining the mass of the cluster and the virial parameter and its size.
Yeah.
And that gives you, how are these stars going to start moving once you set them going. Yeah.
Good. More tutorials. Check them out.
Yeah.
You always want to see what you're doing. So yeah.
Right. Honestly, so this whole thing, I only made this because I was having trouble debugging, because you get all these lovely detailed output from Cosmic, but you're staring at a table of numbers.
Numbers.
You spend enough time and it starts to make sense eventually. But I was like, it would be much easier if I could take any binary from one of these tables and immediately just dynamically produce, this is approximately what its evolution looks like.
Yes.
And this is what figure 2 is demonstrating. So
okay,
it's basically just a one-line thing. You just say, Cogsworth, plot the Cartean evolution of this binary. And here it's just two. Well, I guess I chose a rather extreme mass ratio of, what is that, 18 and 4 solar masses.
Oh yeah, just about.
Which I guess is, because I wanted to trigger a common envelope. So
there you go.
So you can see it evolve along. It changes color as it goes to the Hertzsprung gap. You can see the actual separation of the two stars on the plot is exactly proportional to its orbital period.
Very satisfying.
Yeah. You can see like the time steps. It'll tell you some time steps happen very quickly, where the common envelope, of course, is like, in terms of larger timescales of the binary, very, very short.
Right.
And you can see the orbital separation quickly go from like 647 days to just 10. This is scaled by like the log of the period, I think, which is tiny.
Does this happen dynamically as it runs, or is this like a post-processing?
Which
generating the cartoon?
Oh, the cartoon, it's just post-processing. So like having done the evolution, you'll get a big old table out.
Okay.
It's stored in a cogsworth population, and then you just say binary number whatever plot, and it'll give you this. But it, of course, runs quite quickly. This is all just an matplotlib, so it's just a bunch of shapes in matplotlib. You can see this one ends up with a supernova that disrupts the binary, and some neutron star flying off, and also the main sequence star is probably ejected. I don't know if I wrote that down somewhere, but probably with some reasonable velocity, given that was
Wayne general here.
Period.
Just disrupted.
It would be in the text of it somewhere, but and I think if you go to the tutorial for this one, if someone watching this clicks it, you'll find it's a different binary, because it'll give you just a different one every time.
Good.
It just runs a random binary every time I build the dots.
Shows the flexibility.
And similarly, I don't have plots for these, but you can plot up the galactic orbit of any system just with a single call, and you can plot up a sky map of your whole population using the kind of HealPy package to get it with HealPix coordinates.
Infamous HealPix, yes, Skorsky.
Which is fun, Then this next bit is talking about multi-processing. So
scales.
This is the beauty of the work of Katie and Adrian, that all of their codes are perfectly parallelizable, and so therefore Cogsworth is as well. And this is kind of talking about how the scaling works, and in particular, how to choose how many cores to run it on.
Yes.
So this figure is an example of as you increase the number of processes from left to right here, the runtime on the left-hand side is decreasing. And on the kind of second axis, you can see the kind of speed up that you're getting tapering off. And so as you've got the 8 cores and maybe to 16, you're still getting kind of an optimal speed up from your cores. And then once you get past that point, you don't. This is, of course, dependent on how many binaries do you have and what's the complexity of their evolution and how long are you integrating their orbits. So there's lots of considerations here. So this plot will look different. Your mileage may vary. You should make this plot for yourself and check. But this tells you from this plot for the population that I evolved, which I guess was 10,000 binaries based on the caption. 16 cores is probably you can speed it up slightly, but if you are paying for all your CPU hours, then maybe it's not worth it doing 128 cores. Yeah.
And this is for a fixed amount of works to get whether it's strong or weak scaling, yeah?
Yeah, exactly.
Okay.
Yes.
I'm with you.
I had to read about strong and weak scaling when I was making this plot, but I did learn those things.
Awesome.
Yes.
Very cool. Very good.
Yeah.
Okay. I'll leave that question alone for now. Very good. So that's the scaling.
Yeah, and maybe I should have said with the colors as well. That's basically purple is cosmic and green is Gala. And so you can see that's the kind of runtime split for this population. Again, it varies based on what you do, but in this case, it's like 1/6 of the time is cosmic-ish.
Right, exactly kind of where you're at here, but yeah.
Yeah, rapid pops in. That's
exactly
our aim.
There we go.
Yeah,
it is rapid. Okay. So we got scaling, and what else we got? We got scaling.
Yeah, I think then we go.
How about storage? How much does this all take?
Right. So it all saves just to a single HDF5 file. You can just do like population.save, and then later on you can do population.load. It's very, very simple.
Good.
Using H5Py, which is great. And the size, as I say, the file size of a simulation depends on various factors. It really it matters, of course, how many things you've simulated, how complex they are, because there's a row for each like interesting evolutionary stage. And so you can see, a small population that I use in a later one is only 5 megabytes. And then if you increase it and you have more complex, massive stars, then you're going to have a much larger file. So it varies. But you can kind of, the stuff in the text there tells you a bit more about the things that you should pay attention to if you're worried about the size of your...
Overrunning your scratch space.
Exactly.
we can say that here. It's okay.
Yeah. Certainly never happened.
Citations.
This is fun. I like this. So as I've been saying throughout this, it's really a code that is based on a bunch of other lovely, wonderful work.
Oh, this is awesome. Okay.
And so based on what you have used in your population, it will then dynamically, when you ask to give it the citations, based on the features that you've used and the papers those rely upon, you will get a LaTeX statement to just make your acknowledgements and then BibTeX to go with it.
Very nice.
Because, as I say, it's really based on other people's wonderful work. It's like standing on the shoulders of giants, we should acknowledge all of those people. And this hopefully makes it easy to do.
Right. It's sort of like, when a review article comes out, people just cite the review article, not all the work that went into, creating it. So this is a way of giving this back to the creators of that. So very good. I like that. Yeah. Very nice. Very nice. Okay. And
I think that takes us now into a bunch of examples.
Yeah, let's try using this for something. Okay.
Yeah. So we've got a couple here. Maybe, let's just look at the start section 3 to tell you what's in this plot, and then we'll talk about the plot.
Okay.
So it's basically just a simulation that is exploring how much do you actually need this code? Is it actually doing anything important? And so what this is showing you is the spatial distribution of all of your massive stars at present day.
Okay. Present day.
If you scroll down a little for the caption, I think it'll tell us how long I evolved it for and whatnot. Maybe not. It's in the text lower down, I guess. But it's I want to say evolved for 1 billion years. It's massive stars in a Milky Way potential.
Okay.
And so what I did was evolve it in 3 different ways. Was first just evolve a bunch of single stars. So these ones are just all evolving by themselves without any companions that could move them around. And then if you account for binary evolution, which is the top right quadrant, you can start to see that the scale height of your distribution is changing reasonably significantly. You're getting more stars that are getting ejected out of the plane. You're getting a lot of outliers that are ending up very far away. And so we should probably be considering binaries when we're thinking about our spatial distribution.
Absolutely.
And at the same time, if you do it as, other works have done in the past, not fully accounting for gravitational potential in the bottom right, you can see you also
really going to
very different.
Yeah, it's really going to puff out.
They're going to end up very far away in very strange places. And not so this is basically just taking ejection velocity times time and giving you the distance, which is not great if you have a reasonably strong potential, which is going to decelerate you and move you in different directions.
Okay.
So that's just one example of perhaps motivating the fact that the code should exist in the first place.
Yes. So it answers the question. Yes. If you care about your distributions, your kinematics and placements, then yeah, you need this.
Yeah, you need both.
Okay. Cool. Okay.
Yeah.
So it has now justified its existence. So
which is good. And now the next example is kind of comparing, so the impact of different things here. In particular, thinking about, so if you just go to the start of the second paragraph there, is thinking about doing common envelope efficiency and how it changes the spatial distribution. So this is that parameter where you've got a common envelope, but you've had dynamically unstable mass transfer. You've now got those two things orbiting around within some dense envelope material, which has got some friction. And the question is, how easy is it to unbind that envelope and avoid merging and ending up as two stars afterwards, or just one merged star? This parameter is basically telling you what's the fraction of that orbital energy that you can use to unbind the envelope.
Right.
Okay. What we're going to do is evolve the exact same binary population, but we're going to assume the default choice of 1, i.e. all of the energy is available, and then decrease it by a factor of 10 to 0.1 and say, what if there's actually much less energy available? How does that change our spatial distribution?
Good.
We're going to do this with 2 different galaxies at the same time. We're going to do one for a Milky Way disk potential.
Okay.
And then the other for a spheroidal dwarf galaxy that's supposed to match approximately the Carina dwarf.
Okay. Here we go. Yep. I'm with you.
Exactly. So then we just, sample a bunch of binaries. We assume 100% binary fraction, evolve them for 1 billion years, take all of the massive stars that are more massive than 7 solar masses, and we get figure 5.
Okay. Well, you certainly lost your reticence there for pure binary populations. Okay. Right to it. Figure 5. Oh, I love this one. Okay. Here we go.
And so this is the same style as that plot before. It's got density distributions up to the 95th percentile and then outliers out of that. And this is so if you remember, as Katie was saying earlier, the exact same initial population. It's even down to the initial random seeds, identical.
Okay.
We have just run it in 4 different ways, which is on the top half, running it in a Milky Way disk, and in the bottom half, running it for the Carina dwarf galaxy.
All right.
Left to right, this is changing that alpha common envelope. So decreasing it by a factor of 10 from left to right.
0.1. Yes, I'm with you.
So what do we see? We've got all of our massive stars. And if we decrease the efficiency of this common envelope phase, regardless of which potential you are looking at, you see a significant decrease in the scale height of your massive stars.
Right.
Which is, you can imagine, coming from the fact that if you make this less efficient, less energy is available to unbind the envelope. You end up with more systems that merge.
Yes.
And fewer systems where you've got a situation where the primary explodes and then the secondary can be ejected.
Bang.
So you don't have as many of those runaway situations, and therefore a much kind of more squashed galaxy. And so just by changing this one parameter, you can really shift the spatial distribution of all of your stars.
Yeah. Nice. And what are these? These are kernels or something over here?
Yes. So this is just a 1D kitty on a log scale, just to give you the modular distribution.
Okay.
Sorry.
I'm with you. That's good. No, I'm with you. Cool.
Yeah. And of course, you could achieve this through changing other parameters as well. It is degenerate, but that's why, like I said at the start, you look at different populations and with different dependencies on these same parameters and try and get better constraints.
Good.
Yeah.
Okay. And how about kicks?
Yeah. So I like this next one where we look at the kicks and really how it changes the orbits. This is now not taking an analytic distribution, but demonstrating how you can start to play around with the hydrosims. So what this does is take Fire M11H, which is basically it's like a dwarf-like galaxy with a strong disk component.
Okay.
And we take that, we do the cogsworth thing of fitting a potential to it and grabbing all of the star particles, and then I basically went, okay, let's just take one of them. I just take one star particle and see how it evolves.
Okay.
And so, yeah, you can see the star particles formed, 43 million years ago with a mass of 6,000 solar masses.
Okay.
And then we can sample a bunch of binaries from it, and what you get is this. And so it starts in the bottom left, and I should say galactocentric radius and height. So we're just kind of spatially within the galaxy. Starts in the bottom left and then evolves up to the right. And you can see in the background the unkicked systems, the less colorful ones, what I would refer to as the boring stars.
The gray ones.
But you can see them disperse, right? That's the initial velocity dispersion.
Yeah.
They're not getting any sort of supernova kick, but you do see them disperse over time. And the colorful ones are kind of the fun situations of the situation. Also, getting that legend to have the 4 different colors in it took me an inordinate amount of time for something that's so small, but I am pleased with it. Cheers. So this is now taking individual binaries that have been kicked, and there's a little kind of star symbol where there's a supernova. Then you can see how they kind of evolve. So, for example, like the earliest one that's that like I don't know, dark bluish, has 2 supernovae kind of quickly in quick succession. So we've probably got something that's reasonably equal mass ratio there. There is details in all of the text about exactly what these are, but I'm just going to wishy-washy this.
They're really close, so it's going to be massive star. Okay.
And so those
equal mass, Q equals 1.
Exactly. And so those are exploding quickly after one another, but not disrupting the binary. It stays as a solid line throughout. And so the binary then moves off together, but after the second supernova is ejected from the whole cluster. A different example, the kind of cyan light blue one, that's got a later supernova, so it's something lower mass. But then after that first supernova, there's immediately a disruption where the dashed line is where the secondary star goes, and the solid line is the compact object kind of flying off in a different direction.
I'm with you. Okay, I get this.
Yeah. Later on, second supernova for the other star, and then explodes. Both of them are out of the cluster and in very different directions in the galaxy. 2 stars that were together, separated forevermore. Very sad. But you can see like the green one is kind of a bit more chilled out. That one is really has a late, weak supernova that doesn't disrupt the system, and it stays bound to the cluster.
Right.
And so there's more explanation in the text about exactly what's happening there. But it's essentially that the system was wide enough and the supernova was weak enough that I said that wrong. Supernova, it was tight enough, but the supernova was weak enough that it didn't disrupt it or move it out of the cluster.
Okay. Yeah. So each one is.
I have to say, even though the gray is boring, I love this feature of Cogsworth as well. That you really can track just boring stellar populations, and I think that there's a lot of potential there with comparing to Gaia.
Absolutely.
Just normal stars.
So boring.
So.
Yes. Yeah. And of course, by the numbers, those are by far winning.
Yes. True. Okay. That's a nice capability. Okay.
So I think those are a lot of kind of the main demonstrations. These later ones are maybe for some more specific use cases. So
CMD.
So there's an example of kind of
let's see.
Maybe let's just look straight at the figures. So this is the top one is showing you how you can have your own star formation history. This is demonstrating the one from my paper a couple of years ago. Which, as I say, is heavily based on Nezha's work, but also combines stuff from Joe Bovey and the Macmillan. And so you can kind of see here how where you are formed in the galaxy and your metallicity is correlated because of the kind of inside-out growth of the galaxy and the enrichment as time goes on.
Yes. Okay.
And you can even see in the left one the kind of different components. You can kind of see there's a discontinuity where you go from thin disk to thick disk. In that. And the right one, you can see it as a function of time. So going from very early times, which can give you, a low metallicity. The early times are the bright ones because this is look back time, so it's best. Give you your lowest metallicities, and then as time goes on, you'll progressively increase your metallicity in the galaxy.
So that's minus sign.
That's all there. Yeah.
good. Very good. So we got checking out your own potentials and ooh,
This is a very
excited.
messy color magnitude diagram, which was just basically grabbed from one of the other populations that I evolved above and then said, give me all of the observables. So
Mm-hmm.
this is a mixture of different metallicity from all kind of across the galaxy, which is kind of why it's smeared out like that. But you can still see it's colored by the stellar type of the stars.
Mm-hmm.
Your main sequence stars, which are those kind of yellowy ones. You've got all your white dwarves and all the different shades of brown. And your kind of slightly more evolved massive, or slightly more evolved stars up at the top end with your kind of you're starting your Hertzsprung gap and your giant branch and all that stuff.
Yes, 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 yes. Very cool.
So, and you can dynamically produce that. That's basically you do like cogsworth dot plot color magnitude diagram, and it will make this. So it's should be reasonably easy to do, I would hope.
Did you have as much trouble on this spectral band here on this?
So this I stole because I made this for the Compass methods paper back in the day.
Mhm.
The different pop synth code. I made this color map for some plots that I made for that paper, and so I used the same one.
Very good.
That was much easier.
Oh, good.
Yeah.
Okay. Like any code, you're gonna have a limitations, right? Some
Right.
limits. So let's talk a little bit about that. Or do we want to go down to here? We have some disrupt.
We can probably skip that figure. That one's just kind of showing that you can end up in different places in the galaxy.
Okay. Let's talk a little bit about what some of the limitations currently might be.
Right. So this is all kind of handling isolated binary evolution mostly right now. So it's not accounting for dense situations like if you've got a globular cluster or something like that, where you can have dynamical interactions which can also eject you and throw you very quickly across the galaxy.
Yes.
And so that is not included at all right now.
Okay.
But I will say, like asterisk future work, it is intended to be.
We'll come to that. We'll come to that.
Mhm.
Okay. So, yeah, interactions between systems, subsystems, shall we say?
Yeah.
Okay.
And then this is now kind of thinking of the inverse. So we are thinking about how does changing the binary evolution change where you end up within the galaxy?
Mm-hmm.
And this is thinking about how does the impact of the galaxy change your binary orbit? And so it's
kind of the
assuming
inverse.
that if you have like a wide enough binary, the galactic potential basically acts like a tertiary. And so you've then got a sort of Kozai-Leadov type oscillation, which is going to drive you closer. You could end up with gravitational wave sources or mergers. And that is not currently included in that. I will say we are currently working with the last citation there, Jacob Stegman, add this in as an option for kind of turning it on for wide systems. But it is, of course, quite expensive if you do that. So not for
yeah, nothing for free. Okay. Shout out to James. Okay. And yeah, there's just the uncertainties in stellar evolution, binary evolution.
This is everyone's favorite one, which any pop synth paper should have something in here saying these are approximate parametric prescriptions.
Yes.
Based on original reasonably old. And so we do acknowledge this, and it's something you be wary of. That's why you should use cogsworth in this way of changing all of your fiducial assumptions and seeing how sensitive you are to different things. There is maybe Katie, do you want to talk about Matisse?
Yeah.
Yeah, so we're kind of undergoing a bit of a revolution in the rapid population synthesis community where we've started to move beyond the fits that Ono gave us in 1998. It's time. So we're actively working, myself and Poojan Agrawal, who is the lead developer of Matisse, to get some much needed updated Mesa tracks in the back end of Cosmic here. So we're very much looking forward to that. But currently, Cogsworth is stuck with current Cosmic
Got it.
outputs for now.
Well, you won't see any objection to me for net development. So very cool. Nice. Okay. So we're gonna hang on to we talked about limitations. So the next thing is what we'll talk about. Any final words in the paper itself? We got a little part of the in-list or notebook as well.
Maybe I can take you through this real quick and show you that it's potentially easy to run. So the appendix there is just showing you what a simulation would look like, where you basically just say, import some stuff I'd like to make a population. I'd like to have 1,000 binaries run on 6 CPUs.
There we go.
I'm going to use the star formation history from my paper in the past. I'm going to use Adrian's Milky Way potential.
Yes.
Do that for my velocity dispersion. How long do I want to evolve the systems for? That BSE settings is basically you can pass any cosmic setting that you want to change any of your binary stellar evolution.
Cool.
The sampling params also gets passed into cosmic. You can change your IMF, your period distribution, and then you just have to say create population, and it will give you everything. The data frames of the initial conditions, the full evolution, all the orbits and positions. You can ask it for observables and specific filters. And then you can do all the plots. You can do the kind of cartoon that we saw, but also the orbits and the sky locations and the color magnitude diagram. And then you save it, and it'll be saved to your laptop for later.
Awesome. That is very awesome. Great tool.
Yes.
Really nice tool.
Oh, and maybe one other thing I'll say, because I just noticed on the left-hand side, you see the software section and how there's like 1,000 things in it.
Yeah, good.
And so that is, so maybe I think the last sentence is going over the page, but where it says software citation information, and then at the top,
oh, here we go.
Is aggregated using the software citation station, which is something that I made with Floor Garden to kind of make this easy for you, where you can go through and click all of the individual software that you've used. It'll go to Zenodo, find the versions that you can choose from.
Okay.
Drop down. It'll take all of your LaTeX and your BibTeX. And I think this is now recommended by AAS in their instructions for doing application stuff. So that's my little plug for that.
We like to acknowledge the tools that we use. So very cool. Very nice work. Beautiful. Tom, Katie, thank you so much for walking us through your very awesome software instrument.
Yeah, gladly.
Sure. And I kind of cut you off there as we sort of got toward the end because we talked about limitations because I wanted to save the future stuff till now. So let me ask, where do you think we go from here given the published article? Besides obvious things would be alleviating some of the current limitations, but is there stuff beyond what was in the current limitations that might be of particular interest? Yeah, so where do we go from here?
Yeah, I mean, so yeah, as you say, definitely some of those limitations, implementing some things to go into that would be fun. In terms of code development, I think we've been talking a bit about doing time evolving potentials. So currently it just does static gravitation.
You fix it and you're done, right?
Yep.
But the mass of a galaxy varies fairly significantly over time. And so this could be relevant for long-lived sources. For your massive stars that die very soon, the static potential is fine. But for long-lived sources, we think it could be fun to explore time evolving potentials.
Yeah.
So that's maybe something. And at this point, it's like, here's the code. We want to start doing things with it. So thinking about applications. And there's a few that we're thinking about. Maybe the one that's coming up that we have nearly finished the paper for is thinking about how binaries change supernova feedback in galaxies. So core collapse supernova feedback, because of binary interactions, can be delayed and displaced. So the assumption in the subgrid models that's used in like Fire and Chang'e, for instance, is single star evolution. And so supernovae end after 44 million years, and they all happen precisely where the parent star particle happens. But what you will see, hopefully soon, is some cogsworth simulations demonstrating how at particular times you can still get late feedback. You can get about a quarter of your feedback happening after that time. And you can have feedback in weird locations where, because of runaway stars, they end up quite far away. So
hopefully that's a nice teaser, people. You can go out and check the next paper when it comes out. It'll be very cool. Very cool.
But really, I think we really hope that people will see this and pick it up and use it for their own use cases, because it is extraordinarily easy to use. And so I think we're very excited to see what people come up with, because you never know what ideas are out there.
Oh, yeah. I feel like the most exciting future work is something that we won't do.
That's
exactly. Right. If you give people a tool, they will use it in ways not intended or imagined when it would happen. And
that's right.
Good. That's a beautiful thing. So yeah, very nice. Very cool. Tom, Katie, thank you so much once again.
Yeah.
Thank you.
Awesome. Yeah, and that will do, everyone. And I hope this made your Galactic binary day just a little bit better, and we will see you on the next one. Bye-bye.